Hello everyone, many thanks for joining this, the fifth and final webinar in the Source2C series. My name's Gareth James Lloyd and I work at the UNEP-DHI partnership. We are a United Nations Environment Collaboration Centre and the focus of our work is on freshwater and environmental issues. It's my job to be the facilitator of this webinar today. My colleague Maya, who normally provides technical support, is taking a well-earned break. So my good colleague Chengzi and I will be taking over the job of pressing the various buttons. So please accept my apologies in advance if things aren't quite as smooth as usual, but we'll be doing our best. A little on the Source2C webinar series, perhaps to start. The series aims to highlight the importance of understanding the cross-disciplinary connections needed to achieve SDG 6 on freshwater and SDG 14 on oceans. And in more direct terms, what we want to share and discuss with you is the value of integrating efforts to reduce negative impacts and maximize the potential benefits that are out there. The series has been gathering together a number of expert presenters who share their experiences and knowledge to exemplify the application of approaches based on specific issues. We've been covering a lot of ground in a short time in order to provide some kind of practical overview on the topic, which is something that we found a little bit hard to find. I should also add that the Source2C Management webinar series is developed in collaboration with UN Environment, CHW and the UNDP Water Governance Facility, as well as the Action Platform for Source2C Management. In previous webinars, we've introduced key concepts. We've drilled down into policy and management interactions, as well as something on financing covered in the last one. And if you didn't have a chance to check out those earlier webinars, I'll be sharing those the links with you to those recordings in a short while. Today, in this the final webinar in the series as mentioned, we're pleased to have three experts who are going to be sharing their knowledge and experience. In particular, they're going to be focusing on some of the relevant assessment, tracking and modeling approaches that can be used to help better understand and manage Source2C interactions. Kicking off proceedings, we have Christopher Briggs of the Water Footprint Network. Christopher will be informing us of the value of using water footprint assessments to better understand dynamic flow patterns to the sea. Next up, we have Lars Rosendahl Appelquist of the Coastal Hazard Wheel Platform, and Lars will be introducing us to an approach that can be used to help better govern the critical interface between land and oceans, which is of course the coast, but more about that shortly. Rounding off the presentations, we have Chengzi Chew of DHI, and apart from helping me press the buttons, Chengzi will be giving us an introduction to some of the hydrological modeling tools for various types of planning, monitoring and management. As per previous webinars, we have Birgitta Leimer, our resident expert from the Action Platform from Source2C. Birgitta will be briefly summarizing her broader Source2C reflections based on the presentations, and the idea behind that is that it will help us all to gather our and further frame our thoughts, perhaps. Each presentation is going to take about 10 minutes, and as usual, we're going to allow for 1 to 2 questions immediately after each presentation, just to pick up on anything immediate and break things up a little. We have also, as usual, set some space aside for additional questions at the end from you, the participants. I should probably add right here that unfortunately Christopher has to run and catch a plane in about 20 minutes or so, so he will be leaving us after making his presentation. So if you have any questions, you need to send those in to me as soon as you can under Christopher's presentation. And how do you do that? Well, on the right hand panel of your screen, you should be able to see a box for submitting questions. You may or may not need to just click on the arrow there to expand that. So please feel free to make good use of that. It would be a big help to me if you could identify to whom your question is aimed at, and to keep your question as brief and to the point as possible, and that way it will make it possible for us to cover more ground in the little time that we have. Without further ado, I would like to ask Chengzi to pass control of the presentation over to Christopher so he can begin. Christopher, please could you unmute your mic whenever you're ready, and I will let you know when we can hear your voice and see your screen. Good. Now we can hear your voice. I think I just need to unmute you. Yes, and now we should be able to hear you, Christopher.
Can you hear me?
Yes, we can. So ready whenever you are.
Fine. Thanks very much indeed, Gareth, and very nice to be part of this interesting webinar on Source to Sea. And I hope that my presentation for the Water Footprint Network, of which I am Executive Director, Christopher Briggs, will help a little on looking at the relevance of water footprint assessments for better natural resource management. The work that we do is looking at water in terms of three components. These are ways of looking at how water is used or consumed in producing products, be they cars or cotton or potatoes or trees. And we do this by looking at, first of all, the green footprint, that water which is absorbed through the roots of the plant kingdom and then evapotranspirated or included within the product, like a potato or a carrot or a pineapple, and taken away for sale or use somewhere else. So it is consumed and not available to that area. So that's the green water footprint. The blue water footprint is similarly that water that is used from irrigation purposes or for carrying out irrigation and is extracted from wetlands and rivers and streams and aquifers. And that water again is consumed either by going into the crop and being evapotranspirated or being transported to somewhere else when it is a sheep or whether it is a trunk of a tree, but also when the water is being moved to somewhere else and going into a different water body, or the same water body, but much later on in the year, because both of those mean that the water is not available to the original set of people and stakeholders that could have used that, or the ecosystems that were present there. So lastly, those measures above, the green and the blue, look at quantity. The grey water footprint looks at quality. And it does this by looking at the amount of water that would be needed to actually move or to almost dissolve or associate the pollutants that are present. So by this method, we try and calculate how much water would be used up in assimilating all the pollutants. So it's a measure of water quality. And those three measures are carried out by our team in terms of carrying out assessments. Over a long period of time, we've developed a very large data set from local and international sources. We use, obviously, satellite data, we use agricultural data, and we've been doing this work since the idea of the water footprint was invented or produced by Arjen Hoekstra in the Netherlands, where there was particular interest in water and how it's being used to focus on issues about where water shortages were coming out, how we can better understand the sources of pollution and the reduction of it, and how we can follow the water and affect the usefulness or the efficiency of processes along a supply chain. And it's as relevant for a car as for a cotton t-shirt or as for cows and potatoes and paper. And that's what the main work of the water footprint is to try and get good assessments that are clearly science-based, verifiable, and are useful to companies and countries as they look at the issues of water and how they're using it. And the processes or the stages that we work on is, first of all, to look at the size of the water footprint the green, blue, and grey water. How is it being consumed within the process, the supply chain? Where is it coming from? And when it's being used in the domestic water supply, or it's being used in agriculture, how much of it is being lost to the system because of the availability, the scarcity, and the actual volume used, the footprint that we are interested in looking at. So we need to know all of those, and we need to get the data as cleanly available and readable to a non-technical audience. Next, the assessment is looking at how the water is being used. Is it really sustainable? Does it allow for ecological flow? We allow for 80% of the water to be used for ecological flow, but we also have to consider economically efficient when we see processes of milling or ginning, or we look at production. Is it really using the available and rare fresh water in an effective manner, or is it a little bit wasteful in terms of the way that irrigation or other processes are carried out? And most importantly, is it socially equitable? Is the water that the people need, the local stakeholders, the local people, actually available? Is the conflict between the different users of the water managed in a fair and reasonable system? And that analysis, we look at carrying out a series of recommendations to the company or country that's working with us, and telling them what are the possible actions that they could take, both at the national and the local level, but also what they could do to try and make the situation better for all others. And those are the recommendations that are most important, because they allow them then to move forward in terms of understanding their current needs and possibilities of use in the future. So after a number of years, a number of studies, you can see that here you're looking at blue water availability in the top right over a series of months, how it changes during the year in different parts of the world. And of course, that level of sophistication can be taken not just down to the country, but also to 30 meters or 100-meter plots with sufficient amounts of data that is locally available. Unfortunately, it's not always available in the places that you want, but you have also the idea of the blue water footprint, where you're looking at how much water is being used in different parts of the world over the period of the year. As you can see, it changes. The deepest, darkest blues are the areas where you are most exposed to problems because you're using the most water, and it is not going to be available to the same users later on in the year. So that gives us some sort of picture of where we are. We also have blue water scarcity, where we can measure generally what is available and what is not available, and there are a lot of places that have serious problems of water scarcity, and as we know, as that grows, it increases the pressure on governance systems and on the environment. We think that the analysis of different ways of looking at the system, cutting it by looking at water pollution levels for nitrogen, that can be very helpful to understand where are the pressure points and where we need to act at watershed level or at country level. But most importantly from you, it's important to realize that you can carry out the water footprint assessment at micro watershed level. You can carry it out at 30 by 30 meter squares, and we have done in a number of cases looked at watershed levels. And here is an example of a global study just to show the levels of pollution by two important and common pollutants, nitrogen and phosphorus. That's what you get. Those are the sorts of figures at the global level, but more importantly, we do the analysis right down to farm level and to company and to industry level, and that allows them to make much better use of their water and to understand how it's being used and whether they should be extracting or moving the water from different places or having pre-treatment or post-treatment of their industry. So it's a helpful tool. We work in freshwater principally, and I would hope to be able to move more into freshwater into the marine environment in the future, but we currently have a team that carries out these studies and are pleased to be able to work with UNEP and DHI and other partners. Thank you very much indeed for listening.
And thank you very much for that presentation as well, Christopher. An excellent overview and introduction to water footprinting. As mentioned, we know that you have to run away shortly, but before you do so, perhaps I can give you a couple of questions. The first question.
Sorry. Thanks, Larry.
What is the difference between water footprinting, WRI's aqueduct, and WWF's water risk analysis? All three are different. They're three different tools for analysis, but what is the difference between them, and what is the relative strength of water footprinting?
Well, I think all of them are helpful, and they've derived from the work originally done by the water footprint. The WWF is a close partner of ours, and they've looked at carrying out risk analysis, and it's not done at the same level of detail as we do, and that's the same thing as aqueduct, which is excellent at looking at country or regional level studies to show where there are problems. But if you wanted to say, look at the cotton mills of Bangladesh, or you wanted to see how efficient the processes of water movement were in the Thames River basin, it would be more likely that we would carry out those studies, because the data set and the management of that data has been more of the strength of water footprint. So it's more detailed, working down to lower levels and giving you exact figures that you can work with and decide on how to work with, rather than a more general high-level approach that can be achieved by satellite, but not by having people on the ground actually ground truthing the data as we do.
Thank you very much for that. And a second question, how good is the available data today, and what are the prospects for the future?
The data is good, but it's never good enough. We're now collaborating widely with FAO and with the Dutch government as they are bringing on some more efficient data sets for being able to look down to 30-meter in terms of evapotranspiration, to get data on daily, 15-day, 5-day changes, so we can get into the hands of the farmers and to the policymakers the actual data that is going to help them make decisions about their use of water, rainwater, and blue water, irrigation water. And that whole project, WAPRO, has been extremely helpful in being supported by the Dutch and by FAO, and should give us a good deal more data. But we are getting more and more data all the time. And even if you are in an unknown area, it's quite possible to do very high-level surveys using LiDAR and planes and get the data when you do not have any prior sets of local data, because of course globally one has a lot of approximations, and there's a lot of work done to make sure that one can assess the evapotranspiration rates for any crop, for any type of soil, and those generalizations are put into the algorithms as one makes the calculations. But the data just generally and gradually is improving, and in some cases it's in leaps and bounds, and that is of great advantage to any manager at watershed level, or those that are concerned about pollution and water flow and ecological flow.
Great. So if I could just summarize, and please correct me if I get this wrong, at global and national levels we're in pretty good shape, and also at sub-regional levels we're probably pretty good as well in many cases. But in some regions and local levels, a lot depends on the available data, and there are some holes there, but we are covered in some areas and it's improving. Is that correct?
Yes, if you imagine, we've just done a study for the European Union to look at their water footprint of all the products, all 279 products that they import from around the world. And that showed us whether the data is not at the level that we would really like it to have a degree of certainty. And it is indeed in the countries that you would be most likely to find data shortages would be in parts of Africa and some parts of Asia. But in OECD countries, the data is not a problem. Okay?
Yes, thanks. And I know that as soon as you leave us now, I'm going to be getting some questions about the report that you've just mentioned. But I guess that if we go into the website that's referenced here, we can access all the available materials, I'm sure.
Some of them are easy to find. The new IMPREC study is probably there, but anybody who writes an email to me at christopher.briggs@waterfootprint.org will be very happy to take in contact with you and get you more information about that, because that is an important and interesting study for anybody looking at water.
Great.
Okay.
Many thanks for that contribution, Christopher, and for hanging around to answer a couple of questions. We won't keep you longer, but thanks again and safe travels.
Thank you very much indeed, Gareth. Good luck for all the rest of the presenters, and I hope it's useful for the audience out there. All the very best. Cheers.
Without further ado, Chengzi, could I ask you to pass the presentation over to Lars for the coastal hazard wheel. Lars, as soon as yes, we can see your presentation. We just need you to go into presentation mode and to unmute your microphone.
Yeah, hello, can you hear me?
Yes, we've got you now. Thanks. Please, looks good. Please go ahead whenever you're ready, Lars.
Great, thank you very much. Yeah, so I'll talk about how to boost coastal governance in a changing climate with a new coastal hazard wheel system. And I'm from the Coastal Hazard Wheel platform that basically functions as a coordination hub for all activities on the coastal hazard wheel system. And in this presentation, I'll give a general introduction to the whole coastal hazard wheel and how it works. Then I'll talk about how it can be applied for multi-hazard assessments at local, regional, and national level. Then I'll talk about how it can be applied for identification of hazard management options. Then I'll talk a bit about how it can be applied as a standardized coastal language. And finally, I'll touch shortly upon the Coastal Hazard Wheel app and the Global Coastal Classification Program. So firstly, I'll talk a bit about the whole functioning of the Coastal Hazard Wheel. And basically, the Coastal Hazard Wheel is a universal coastal management system, and it can facilitate source-to-sea governance as it covers all coastal environments globally, basically including inner delta areas, estuaries, back barriers, outer coastlines, and islands. So basically the whole inner parts of the coast to the more outer shelf somehow. And it can be used to manage a full range of hazard types at the same time, and it can be used for climate change adaptation and for disaster risk reduction. And finally, it can also be used as a standardized coastal language to help bridging the gap between scientists, policymakers, and the general public. So in short, one can say that the Coastal Hazard Wheel functions as a key to understand why a coast looks and behaves as it does, to identify the full range of hazards to a coast under a changing climate, to identify what are the relevant management options, and to communicate information to relevant stakeholders. And the Coastal Hazard Wheel basically divides the coastline into 200 to 300 meter sections. So therefore, it can be used both at very local level and scaling up to complete global level. But of course, it also depends on data availability of the accuracy of this use. And one can say that the Coastal Hazard Wheel functions as a multi-tool, and then it can be supplemented by relevant process models or engineering calculations where appropriate. So it's somehow a first-line system to tackle all coastal challenges at the same time, and then it can be supplemented with relevant approaches, tools, and models whenever relevant. So the Coastal Hazard Wheel itself is based on a new coastal classification system. And the classification system is developed to obtain an appropriate balance between simplicity and data inputs and relevance for decision support. So this is, of course, a neat balance to strike. And it includes the dynamic interrelations between the main biogeophysical parameters present in coastal environments globally. And all the subcomponents of the coastal classification system has of course been clearly defined, but I won't go into more details about this now, but it can be found on the coastalhazardwheel.org website, and more specifically in the quick start guide. So the Coastal Hazard Wheel consists of generally 6 coastal classification components, which are the geological layout of a coast, the wave exposure of a coast, the tidal range, the flora fauna, the sediment balance, and the storm climate, and the interactions between all these. And together, all these components generate a coastal environment, you can say, and inside this coastal environment, different human activities are taking place. So if you take a look at the coastal hazard wheel, so this is basically the coastal hazard wheel version 3.0, so this is a fully functional version ready for global use. And it consists of 6 coastal classification layers, which are these ones, these circles, going out here. Then it consists of 5 hazard layers out here. Then it has the coastal classification codes out here. And in total, it has 131 different generic coastal environments, and in total 600 of 55 of specific hazard evaluations out here. So it has a lot of information somehow pressured into this system. And if you go a little more in detail into the build-up of the coastal hazard wheel, then we have the coastal classification layers, where we have the first circle here, that's the geological layout. Then comes the wave exposure circle, then comes the tidal range circle, the flora fauna circle, the sediment balance circle, and the storm climate circle. And then comes the hazard layers, where the first layer is ecosystem disruption layer, then comes the gradual inundation, saltwater intrusion, erosion, and flooding, and then the coastal classification codes out here in the end. And basically one uses a coastal hazard wheel by starting here in the wheel center and then moving outwards, so you could have a sediment plain with moderate wave exposure, then any of these conditions, because they're not important in this coastal environment. Then you have sediment balance, and you have storm climate, tropical cyclones presence, and then you end up with a coastal code, for example, PL5. So you can do this for any coast in the world, basically. And if you take the coastal hazard wheel, then each coastal environment will look the same way and have the same core characteristics anywhere in the world. So if you, for example, take an example of a FR16 coast, which is the one out here, then this is an example of a FR16 coast. And this is a coast in Chambiani in Zanzibar, and all FR16 coasts will look relatively similar to this coast here. And if we take another example, we could take a DE21 coast type, which is this one, and it looks like this. This is from the inner parts of the Bangladesh Delta, a place called Bakali, and all DE21 coasts will look relatively similar to this image here. So somehow it also captures the core characteristics of all coastlines worldwide, along with the hazard profiles and management options. So now I'll talk a bit about how the system can be applied for multi-hazard assessments. And basically it can be used for multi-hazard assessments at local, regional, and national level, and both for screening purposes to identify hazard hotspots, and for more accurate hazard assessments that can support even local management decisions. And it can be carried out both manually in ArcGIS or by using the automated coastal hazard wheel app that is undergoing continuous development. And generally, a standard assessment using the coastal hazard wheel provides information on all the 5 different hazard types, namely ecosystem disruption, gradual inundation, saltwater intrusion, erosion, and flooding. So you get this whole package all in one go somehow when you use it for assessments. And this is an assessment carried out for IFAD for Djibouti, and more specifically Djibouti City in ArcGIS, and then extracted to Google Earth for flooding hazards in Djibouti City. And here you can see this gives a pretty good overview of where are the flooding hazards in Djibouti City. You can see the red are the very high flooding hazards, then you have the yellow are moderate, are high, and the blue are moderate hazard level. So you can see it gives a pretty good indication of where is action needed in this area for tackling flooding hazards. And of course you can get the similar maps for erosion and ecosystem disruption and so forth for the other hazard types. But this is carried out as a manual assessment. It can also be carried out as an automated hazard assessment. This is an automated hazard assessment for the whole coast of Bangladesh, including you can see the inner delta areas, the east coast, the full east coast of the country. And this is taken from a test from some of our automation R&D activities. So somehow it's not very accurate at local level, but it just gives a good picture of where are the hazards present. This is the hazard for erosion. And you can see it gives a pretty good overview of the hazard hotspots. Where are the very high hazards? Where are the high and moderate hazards? And this can be used as a first identification of hazard presence somehow. And then of course it can be model more in detail, so you can use it for even local planning. But this is from a R&D assessment at this more national level. So it can be used both at local level and national level, depending on requirements and needs. And then I'll touch upon the application of the coastal hazard wheel for identification of hazard management options. And basically, it can be used for identifying relevant hazard management options for a coastal location. And it can be used for spot assessments at any coastal location worldwide for a specific coastal spot. Or it can be used to guide more broader management discussions and decisions at regional, national level, or within the broader source to sea system, including, inner deltas, back barriers, and more outer coastlines to capture the whole system altogether. And to identify relevant management options, the system uses this matrix, which contains, I can point an arrow here, all the main coastal management options listed here for the different hazard types listed here. You can see ecosystem disruption, gradual inundation, saltwater intrusion, erosion, and flooding comes out here. So it covers all the main management options for the different hazard types. And then the coastal classification code is used as entry here. And you can go in and identify any relevant management option for this specific coastal type. You can see a PL12 coast, and you can see what can be done here to tackle gradual inundation and these issues. And then you can furthermore go into this and see what is the catalog number in the UNEP-DHI publication, where all these different management options are described in more detail. So if we take an example of how this is used, we can take a well-known example, which is Miami Beach in Florida. Most people know this place, so it's not such a surprise that that is a quite hazard area, but still is an interesting example. So if we take the outer barrier of Miami Beach here and use the coastal hazard wheel to classify, then we classify the coast and say the geological layout, that's a barrier, that's the inner coast here. On this wheel here, then they have the wave exposure as exposed. Then you have tidal range and flora fauna are not of significant importance for this coastal type. Then the sediment balance is balance deficit, and the tropical cyclones is a yes as tropical cyclones. So the outer coast of Miami Beach is a BA1 type. So this is basically this one in the coastal hazard wheel. And then you can go further and identify the hazard profile for this BA1 coast. And you can see here it has low and moderate hazards for these hazard types, but very high hazards for saltwater intrusion, erosion, and flooding. And this is, of course, not such a great surprise for Miami Beach, but in many other areas it can be quite useful, and especially for the hazard mapping. And then you can go further and see what can be done in this area. So you have the BA1 type. He has combined a few types together because they have similar conditions, but that's described further in the guide. But basically you have the coastal type, and then you can see what are the relevant management options to tackle the different hazards, where these hazards were the one with very high hazard levels, so they are especially important. And then you can go into the catalog and see, okay, we have is relevant to do dune construction and rehabilitation, and that's further described in the UNEP-DHI catalog chapter 7. And then you can get further guidance on how to do this dune construction rehabilitation. So basically it's the whole key where you can do the hazard assessment, identify management options, and get further guidance on the management options. And then finally, it can be used as a standardized coastal language between the broader group of coastal stakeholders. And generally, you can say that the coastal classification codes out here, the outermost codes, can be used for standardized communication between different coastal stakeholders. So you can say, I'm in a FR18 coast now, and then everybody would know exactly how it looks and what is the hazard profile and what can be done in this coast. And the full coding system includes codes on socioeconomic activities and implemented hazard management measures, but that's not displayed here, but that's further described in the UNEP Quick Start Guide. But that is added on to this main code. So basically you have the main code here, and then on top of that you add information on socioeconomic activities and what has been implemented of management measures, and then you get a full language for coastal communication. And that can facilitate communication across the larger source-to-sea system, and can also help boosting multi-stakeholder coordination and communication at many different levels, at sub-national level, or between local to national level, or national to international level, and so forth. And the full complete coding system is available in the UNEP-DHI publication that's published this year, which is available at the website coastalhazardwheel.org. And finally, then I'll briefly talk about the Coastal Hazard Wheel app, which is an automated...
Sorry, Lars, 1 minute, please.
Yeah, sorry?
Thanks. Just 1 minute left, yeah?
Oh, yeah, no, sorry, this is just, I just need 1 minute, so don't worry, Gary, it's perfect. So basically, the Coastal Hazard Wheel app is an automated system for classifying the world's coast automatically and providing information on adaptation, adaptation guidance. And this system is undergoing continuous development, and now it's the first version of it, you can say, is available. And over the next years, it will be continuously refined and developed, and global coastal classification data will be provided with open access. Yep, that's it, Gary. Thank you very much.
Yeah, thanks, and sorry about that, Lars. I know how enthusiastic you are about coastal hazard wheel work, and I am too, actually. And that website you mentioned, that's the place to go to see the various tools, guides, information portal that you've mentioned there. A quick question for you, just before we moved on. To many people, it might seem remarkable that this kind of classification system or something like it isn't already available. But what is out there? What do people currently do?
I mean, you can say that there are different coastal classification systems available, but not somehow this all encompassing system that just captures all the world's coasts at a very local detail level at these few hundred meters. I mean, there are this general, geomorphological classification, systems, but more like, delta classifications, for example. There's a famous delta classification triangle for classification of deltas, and there are classification systems for identifying, barrier coasts or different subcomponents of this coastal system. And then there's a more engineering approach to coastal classification that's developed by one of your colleagues, Gary, called Carsten Manker. He's a grand old man in the coastal world somehow, and he's developed a more engineering coastal classification system for mainly straight coastlines for design purposes, to how to design barriers or breakwaters and these kind of things. So you can say this is a first line complete classification system that captures any coastal conditions worldwide. And then, of course, you could use specific classification system like the one developed by Carsten Manker for more engineering considerations, and you can use different modeling approaches to design specific management measures and these kind of things. But somehow there's not a complete real global coastal system available in this way as the Coastal Hazard Wheel at this point.
Okay,
but somehow it should be mentioned that. That's right.
Yeah, thanks, Lars. We've got to move on, but please hang by. If you could put your microphone on mute, we will come back to you. Chengzi, if I could ask you to pass over the presentation to yourself, and I can let you know when we can see and hear you. Yeah, we can see your presentation, and now we can hear you. Yes. That all looks good. So please feel ready to start whenever you like.
Yep. Many thanks for listening in. My name is Chengzi, and today I'll be talking about modeling tools from source to sea, and in particular deterministic modeling tools from DHI's perspective. Before I dive right in, I would just like to say a few words about DHI. DHI is an independent, private, not-for-profit research-based organization. We operate in more than 30 countries, and our headquarters are in Copenhagen, Denmark. Our core business areas is in the water environment, and that ranges from rivers, reservoirs, cities, to marine and offshore areas, pretty much from source to sea, you may say. Our competences are in modeling, from numerical modeling to physical modeling. And we've invested a lot of resources in improving these modeling software tools so that many others are able to model the world of water. So I'm very happy today to be able to share some of the ideas and the modeling tools that we have. Let me start off by very broadly explaining what numerical or computational models are. They're basically a set of algorithms or equations used to capture the behaviors of a system. And these systems can be any type of systems, from physical, economical, biological, hydrology, hydrodynamics, and so on. And broadly speaking, there are two kinds of numerical models, deterministic and non-deterministic models. What are the differences? A deterministic model is essentially a set of formula. Take, for example, 2 + 2 = 4. This is the formula that always gives the same answer when you provide it with the same inputs. In more complex deterministic models, such as those in hydrology and in hydrodynamics, the model is often represented by a set of differential equations. And these equations are usually not solvable. However, they can be approximated. And this is normally done with a discretization scheme. And the accuracy of such approximation depends very much on how the discretization scheme is set up, what we call the model setup, and what kind of inputs or data you add to the scheme to approximate the solution. Therefore, when we use models to evaluate certain scenarios or decision points, we have to be aware that the outputs from the models are by default an approximation of the actual system. But there's still many uses for such deterministic models. They're used mainly to support decision making, especially when you have to make a choice of a few different options. What about non-deterministic models? On the other hand, they are sometimes called a black box model. And these models are usually probabilistically driven. And the outputs are usually calculated with some kind of probabilistic elements. They may not give the same outputs with the same inputs, but they have their uses as well. Mostly, they're used in risk management and risk mitigation. For example, if you want to find out whether an event has a chance of happening or not, very much based on past events, these models can provide an estimate of that probability. And of course, non-deterministic models can be used in combination with deterministic models, and where deterministic models provide the data which is very much needed for these models to operate. Talking a bit more about non-deterministic models, there's no doubt a recent boom in this application of such models. You may have heard the terms machine learning, artificial intelligence, and so on. And in our view, these are considered non-deterministic models. Machine learning is a special type of non-deterministic models where it mines data and it tries to recognize a pattern in the data set. And this can be done in various ways, but especially with artificial neural networks. Given the large amount of data available that we are producing every day from social media, Internet of Things, devices, and so on, and increasingly affordable access to cloud computing, machine learning has taken a very big step in many of the different applications that we see in our everyday lives. We haven't seen so much of these applications in the water sector yet, but I think it'll be very interesting to see what's coming in the very near future. Moving on, like I said earlier, the presentation today will be very much focused on the deterministic modeling tools, and there are many types of these tools around. And I hope to be able to give you an idea of what tools they are available. Let's start off with river basin modeling. Most river basin modeling tools are conceptual. And that means that each catchment in a river basin can be viewed as a bucket. And one bucket can connect to many different buckets to form a river basin. Such tools, even though they are conceptual, they are designed for analyzing water sharing issues at international, national, or even local river basin scale. and they can be used in many different applications within the river basin field. Key application points are optimization of reservoir and hydropower operations, or assessing climate change impacts on water resources availability and quality. For actual river channels modeling, there are more specific river modeling tools. In this example, I'm showing Mike Hydro River, and it's of course one of many such river modeling tools around. River modeling tools, they can be considered a one-dimensional flow tool. So water is assumed to be flowing only within the river channels, and so on. And that is one-dimensional. And it is designed to model a variety of tasks related to river hydraulics, water quality, flooding, forecasting, even navigation, as well as catchment dynamics within the river. When we look at from the view of a source to sea perspective, we should not neglect the groundwater as well, and there are many different groundwater modeling tools as well. If you want to focus more on groundwater issues, this is the tools that you should use. This example is FeeFlow. It's a groundwater modeling tool that uses finite element calculation techniques to handle a broad variety of physical processes. And tools like that are designed to model groundwater flow, contaminants within groundwater, groundwater age, and even the heat transport within groundwater. One interesting fact about such models is that it's sometimes even used in the design of dipools. And one could imagine that dipools are very much similar to kind of a groundwater setup. So you have different layers of soil or texture that the water flows through. Moving on from rivers, we now go on to cities, and there are definitely many different tools for cities, and most of the modeling tools for cities are designed for water networks. We have an example here called Mike Urban, and it is a tool for water networks in a city, including water distribution systems, stormwater drainage systems, as well as sewer collection systems. Such tools are usually used for master planning of water network systems or sewer collection systems, as well as to optimize these networks on how they operate, and also to look at where leakages are, where there's a risk of contamination, or where there's a risk in changing water quality, and so on.
2 minutes, please, Chengzi.
Yeah, finally, we come to the sea, and there are 2 or 3 dimensional modeling tools to model physical, chemical, or biological process in coastal and marine areas. If you're looking at surface flow analysis, for example, oil spills or flood analysis, maybe a 2D tool is sufficient. But if you're planning to look at flows within the water column in the sea, then we will recommend a 3-dimensional flow modeling tool, and these tools are designed for analysis of different structures in coastal offshore areas, design of front ports, layouts, and even marine infrastructures in the sea. So I've gone through a number of different modeling tools, and each modeling tool has its own application niche. However, it's not uncommon to combine them. So one example is flooding. If we look at flooding, there are many reasons why flooding occurs in, for example, a city. It could be due to an overflow of rivers, it can be due to overflow of sewer collection systems, or it can be water coming from the sea. And if you want to have a more detailed look at the different aspects of such flooding scenarios, then you could combine, for example, 3 different models to look at how flooding can be prevented in such an area. So to sum up, these are all the tools around. I think there are many more. It's therefore very important to understand what kind of issues you want to analyze, and choose the correct modeling to do that. And if you want to combine the results of different models, it's also important to look at how these models can be interconnected. And while choosing these models are important, it's also important to understand that they're all mathematical models. They are driven by data. It is important to find out whether you have the available data sets when it comes to modeling, and whether whether it's easy to set up, and whether there's a community or whether there's a prize and training support for using such a tool. So that concludes my presentation. Thank you very much.
And thank you to you as well, Chengzi. A quick question for you before we move on to Briggs for the summary. How can you determine the accuracy of these modeling tools? How is that achieved?
The most common way to find out the accuracy of a model is to go through the kind of the proper modeling workflow. And there's a step what we call a calibration and validation step. And what one does in this step is to check the output of a model with known results, for example, a historical flood event, and see whether the outputs match. If it doesn't, then one changes the variables in the model setup to kind of calibrate the model, and then we check again. And when you repeat this process, you kind of increase the accuracy of the model. When you don't have those data set, then it's a little bit difficult to check that accuracy.
Right. Thanks for that, Chengzi. I guess that's a standard process for all types of models. Please don't run away. Again, we'll be coming back to you. But if you could change the presenter back to me, please, then I can continue. Yes, show my screen. How's that looking, Chengzi? Can you see it?
Yes.
Great, thanks for that. So just to move on, as you can see on the agenda, we now have Briggs. And Briggs, if you could please unmute your microphone, we would like to hear your thoughts on what you've heard so far in relation to source-to-sea work.
Thank you. Can you hear me?
Yes, we can hear you well. Thanks.
Excellent. Yeah, so thanks for 3 very interesting presentations. It's of course very complex to understand and track and model source-to-sea interactions. They're complex, often slow processes. There are many different types of interactions. I think in the source-to-sea concept that I presented on the first webinar, we have tried to define the different source-to-sea interactions as the flows of water, sediments, pollutants, biota, materials, and ecosystem services that connect kind of upstream system with downstream systems. And of course, these are often very slow processes, and they're influenced by many different factors, and they're crossing through many different subcomponents in the source-to-sea system. So obviously, it will be hard to have like one source-to-sea model, one tool to assess interactions and dynamics in source-to-sea systems. So I've been very interested to listen to these 3 different types of analytical tools to understand the interactions within. The first, the water footprint, to understand the relationship between water use, water pollution, and water availability. And thinking of source-to-sea, also the connection to ecological flows and impacts on marine pollution, perhaps. The coastal hazard wheel, very interesting to understand more the classification or how you can characterize different coastal types and come up with management options for those systems. It would be very interesting to have also a similar type of classification for different source-to-sea systems, but I have a feeling it would be a very big wheel, considering how diverse they are. And also very interesting to listen to the different types of deterministic or undeterministic models. It took me back a bit to my engineering studies back in the days.
No, thanks very much for that, Birgitta. I kind of agree to what you alluded to and what I said in the introduction. We're covering a lot of ground in a short space of time and trying to give a flavor of, I think during the course of the webinar series, we've been everywhere from the high level policy, and now here at the end, we're down into the nuts and bolts. Well, if you want to kind of manage at an operational level, it's all about measuring and monitoring and being aware of what processes are ongoing in order to influence them. So thank you very much for that, Birgitta. I would like to now go back to Lars and Chengzi. If you could both unmute your microphones. I've got one eye on the time here, so I think we'll make it quite quick. Whoops, I can see that I'm having a couple of technical challenges with my screen. Does that look okay, Chengzi?
Yes.
Okay, good. But I'll go to Lars first, if you're there, yeah. Lars.
I'm there.
So you mentioned that this coastal hazard wheel approach gives a common approach or even a common language. Actually, I mean, of course, the presentation was in English. That's what we asked you for. But what other languages are available out there? You know, if I want to use it in French, do you have something?
Yeah, I mean, basically, the coastal hazard wheel itself has been translated to all the official UN languages, which is like English, French, Spanish, Arabic, Chinese, and Russian. And that's the core coastal hazard wheel, and that's part of the what's called the executive summary of the UNEP-DHI publication, which is also available on the www.coastalwheel.org site. And in the future, we hope to be able to translate the quick start guide also to some of these UN languages, or even to a broader language group somehow. But as a first step, the coastal hazard wheel is available in these 6 UN languages, and then further translations will probably be carried out in the future.
Yeah, thanks, Lars. And another quick one for you. I mean, you gave the example of some very clear examples, but I guess there are also situations where one could be in doubt about what the classification of a specific location would be. What advice would you give there for someone who's using the coastal hazard wheel?
Yeah. I mean, that's somehow, you know, a classical challenge of most natural science classification systems. Like in soil science, you have also these border areas where it's difficult to classify or determine whether it's in one category or on the other, or cloud classification systems and all this. So somehow, I mean, the system is made in a way so if you have a coastline that could fall into a few categories somehow, in most cases that would end up giving the same hazard profile and same management options, more or less, somehow you can say. So if you carry out the classification manually, you would have to do the best judgment and then decide on the option you find is the best choice. And it wouldn't have such a great impact which of them you choose. And on the automated system, of course, that would provide the information automatically based on some criteria we have set up. But that's, of course, work in progress to get it correct and detailed.
Yeah, many thanks for that, Lars. Chengzi, over to you.
Yes.
A little bit of a broad question here for you. I mean, in 2 parts. How do people tend to use these modeling tools today? And in your opinion, you know, where are we going in the future? What's going to happen or could happen if you put your fantasy hat on with a high dose of reality?
Yeah. The first question on how people use it, I think the more traditional way of using models like that is to do some kind of assessment. If you have, let's say, 2 scenarios or 2 solutions to a possible problem, for example, flooding, you might choose to build a dike, for example, or you might choose to expand the sewer system, for example, or do both. And what you use the modeling tools then is to find out what is the impact of these options, and then you do a cost-benefit analysis and find out which are the best decision to make. Other ways of using models could be in a more operational part of it. So, for example, in Copenhagen, we have a bathing water system. So we want to find out whether it's safe or not to be bathing in the sea. And we have numerical models that runs that, you know, every day, and one can download an app and go online to see whether it's safe or not to swim right now. And that is a little bit more hidden in that sense. And I think these are two examples of how we use models nowadays. Thinking a little bit more into the future, I think there will be we will catch up with all this cloud computing and big data, and I think in the future the models will be very much connected to a lot of different systems. So we might be able to get data from different streams more easily, and we'll be able to run models quicker, and it will be more accessible for more people.
Many thanks for that, Chengzi. I guess that, an obvious thing would be linking to, or greater linking to climate models, and of course the rise in the use of satellite data for source to sea type work. But thank you to both you and Lars for that. I'm afraid that's all we've got time for in the way of questions right now. For those of you, for those that we didn't have time with regard to questions, we're going to be liaising with the presenters and we'll get back to you with a response. So please don't feel left out. As mentioned, this is the fifth and final webinar in the series. Here is a list of all the webinars, as well as a link to the recordings and presentations. You can find all the earlier ones here, also via YouTube. And I aim to get this one up and running on the website, this fifth one, early next week also. While this session concludes the webinar series, the work of the Source to Sea action platform continues and is going from strength to strength. And if you'd like to learn more about the platform, please check out the link here. And this is also the place to get access to Birgitte's contact details for more information if you require it. If you have any burning questions or issues, please send an email to Maya. She's going to be back in a couple of days, and she'll either get back to you directly or share them with the presenters for a response, or myself, of course. And as usual, I always say we're always looking to improve the quality of our work, so we'd be very grateful if you could use a couple of minutes to respond to the feedback survey form, which you'll receive automatically when you close down this webinar. Finally, please allow me to conclude today's presentation as well as the series by thanking all the presenters for taking the time to join and share their knowledge with us. And I'd also, of course, like to thank you, the participants, for taking the time to join us today and also during the other sessions. Please let me wish you all a very good morning, a good afternoon, and a good evening, wherever you are.